Hello everyone. Today let us discuss the topic magnetic field on the axis of a circular current loop. Here I have shown you the picture of this circular coil which is carrying the current. The current is in this direction which is shown in this picture. This is the direction of the current I. Now let us evaluate the magnetic field due to this circular coil along its axis. This is the axis, okay? So this is the axis. This is the axis, that is OP. This is the distance of the point P. OP is, that is equal to x, is the distance of the point P from the origin. Then axis of the circular coil is OX. Axis of the circular coil is OX, that is the x-axis. Now we want to find the magnetic field at the point P because of this circular coil, carrying a current I. And we have taken this, everything is evaluated in the free space. Free space means, excuse me, free space means the permeability will be mu naught. Permeability is mu naught. So we are taking the free space. Now let's continue. Yes. Now if you see here, in this figure, the circular loop carrying a steady current I. So you can see here, this is the direction of the current I. The loop is placed in the YZ plane. So this is the y-axis and this is the z-axis and this is the x-axis, and our loop is placed here with its center at the origin, and it has a radius capital R. The x-axis is the axis of the loop. X-axis is the axis of the loop, and we want to calculate the magnetic field at the point P on this axis. We want to calculate the magnetic field at the point P. P is at a distance of x from the origin O. Now let us, instead of calculating for the whole loop at a time, first we will calculate for a small current element dl bar. So dl bar, we have taken on the top of this loop a small portion dl bar. First we will calculate the magnetic field because of dl bar at the point P, and then later we will integrate it to get for the whole loop. In most of our derivations, we do like this only. First we will calculate for a small part, then we will integrate it, then we will get for the full part. So here also, instead of calculating for the whole circular loop at a time, first we will calculate for a small portion dl bar, and then we will calculate for the full loop by integrating it. dl bar is there on the top of this loop. From dl bar, the point P is at a distance of R. R bar is the position vector from dl bar to P, from here to here. So here you can clearly see the distance between the point P and dl is R. Then according to Biot-Savart's law, the magnetic field at P due to dl bar is equal to, in magnitude form, dP is equal to mu 0 by 4 pi I dl r sin theta by r cube. But in vectorial form, if you take dB bar is equal to mu 0 by 4 pi I dl bar cross r bar in modulus divided by r cube. This is Biot-Savart's law. dB bar is equal to mu 0 by 4 pi I dl bar cross r bar divided by r cube. I have explained Biot-Savart's law in my previous video. Let it be equation number 1. Now dl bar is the small current element. R bar is the distance from dl bar to the point P. So let us further continue. Now you can see here. Now if dl bar is here and r bar is the position vector, dl bar and r bar, they are perpendicular to each other. Any element of the loop is perpendicular to the displacement vector. any element of the loop is perpendicular to the displacement vector from the element to the actual point. In simple words, to make you to understand, dl bar and r bar, they are perpendicular to each other. Then dl bar cross r bar, it is a cross product. It becomes dlr sine 90, because dl bar and r bar are perpendicular to each other. Sine 90 is equal to 1, therefore it will become dlr. It will become dlr. So dl bar cross r bar is equal to dlr sine 90, which is dlr equation number 2. Let it be equation number 2. Now let's further continue. Let us take the triangle. Let us take the triangle OAP. Let us take the triangle OAP, that is right angle triangle, which is 90 degrees at origin. Therefore, let us apply the Pythagoras theorem, that is r square is equal to x square plus r square. You can see here hypotenuse is r. This is one side, this is another side. Therefore, we will get r square. R square is equal to x square, that is small r square, is equal to x square plus capital R square. Let it be equation number 3. Then substituting equation 2 in equation 3, substituting equation 2 and 3 in equation 1, we get, what is equation number 1? Here is the equation number 1, Biot-Savart's law. dB is equal to mu 0 by 4 pi IDL cross r bar divided by r cube. Let us substitute in that. We will get that dB is equal to mu 0 by 4 pi IDLR. That cross product has become DLR sine 90, which is DLR. Therefore, ideal cross r bar will become DLR. Then after that, divided by r cube. This r cube I am writing as r square into r. Then r square into r. Then what happens here is, in the numerator 1r and denominator 1r cancel, and you will get mu 0 by 4 pi IDL by r square. So we will get finally dB is equal to mu 0 by 4 pi IDL by r square. But r square we have seen here x square plus capital R square. Then we will get to dB is equal to mu 0 by 4 pi IDL divided by x square plus capital R whole square. So this is equation number 4. So let's continue. This is equation number 4. Let us continue without wasting much time, because it's a very long derivation. Then the direction of dB is perpendicular to the plane formed by dl bar and r bar. We all know that from the beginning. Direction of the dB bar. Please look carefully. You can see there. This is the direction of the dB bar. DL bar is like this. This is DL bar. R bar is like this. They both are in one plane. Then once again I will tell you, DL bar is in this plane, say for example. Then R bar is like this. They both form one plane. Then the direction of the magnetic field will be perpendicular to the plane containing both of them. This is the direction of the dB bar, which I am showing here with the red color arrow. Then we resolve the components of dB bar. Let us resolve the components of dB bar. Along x-axis it is dBx. Along y-axis it is dby or dB perpendicular. dBx is the component along x-axis, and dB perpendicular is the component along y direction, then perpendicular to that. Then what happens here is, if you resolve the full circle, that is the full circular coil, so I'll show you here. On the top we have taken one DL bar. Because of that, the y component will be in the upward direction, exactly opposite to DL. Down another DL will be there. So because of this lower DL, which is of the same size and exactly in the opposite direction, then the magnetic field y component, because of this lower DL, will be magnetic field of the y component of the magnetic field because of this lower DL will be downward direction. Therefore upward arrow, that is DL bar because of top portion, DL bar because of down portion. That means I will show you here with some this one 1 and 2. 1 is the DL bar on the top of the circle, 2 is the DL bar on the bottom of the circle. Then y component DL perpendicular because of the 1 and y component because of the 2 which is below, they cancel out each other because they are equal in magnitude but exactly opposite in direction. I hope you understood that, because all the y components, they cancel out each other, because you can take one DL here, another DL here, another DL here, another DL here. So you can take another DL here, another DL here. So these two are opposite. If you take another two DLs, these are opposite. Yellow and yellow, blue and blue, red and red. So this green, yellow and yellow. So again I'll draw some green and green. So all these are opposite components. Their y components, they cancel out each other. All the y components, they cancel out each other. What will remain is only the x components. Therefore, the net contribution along x direction can be obtained by integrating dbx is equal to db cos theta, because only x components will survive. For 1 DL, it is db cos theta. Then we want for the whole circle, then we have to integrate this db cos theta. Then we will get for the full circle. Before going for the full circle, let us take this one, that is a triangle OAB, triangle OAP. Let us take the triangle OAP. Therefore, here cos theta is equal to, here you get theta, where I am showing there, or else I will use another color. Here is the blue color one is the theta. Then cos theta is equal to capital R divided by small r, that is adjacent side divided by hypotenuse. Then small r is equal to, according to Pythagoras theorem, small r is equal to capital R square plus x square whole is under root. That means r square plus x square whole to the power of 1 by 2, whole to the power of 1 by 2. So we are getting like this. Okay. So now this is the formula which we are getting. Then let's continue further. From equations, let us take it as equation number 5, which I have shown here. So equation number 5. Now let's further continue from equations 4 and 5. So what is equation 4? Let's go back and see. This is equation number 4. This is blue color one is the equation number 4. And then equation number 5. This is equation number 5. This is the equation number 5. Then from 4 and 5 we will get mu 0 by 4 pi IDL, mu 0 by 4 pi IDL divided by x square plus capital R square cos theta. So this is the one 4 and then this is the one 5. So from 4 and 5 we will take dB x is equal to dB cos theta. dB means equation number 4, this one, and dB the cos theta means equation number 5. Substitute them 4 and 5 in that dBx is equal to dB cos theta. We will get mu 0 by 4 pi IDL by x square plus capital R square and cos theta. Now let us substitute the value of cos theta and see now what happens. Here I have substituted. You can see here dBx is equal to mu 0 by 4 pi IDL by x square plus r square capital R by x square plus r square whole to the power of 1 by 2. This is the value of cos theta which we got in this previous page. So this is the value of cos theta which I am circling here. So then let's proceed. Then this cos theta value is substituted here. Then if you see the denominator, what you are going to get x square plus r square, here x square plus r square whole to the power of 1 by 2, then 1 plus half the power which is equal to 3 by 2. Then you are going to get dBx is equal to mu 0 by 4 pi IDL r by x square plus capital R square whole to the power of 3 by 2, equation number 6. Now when we integrate this particular formula for the full circle, integration, in the integration what happens is, I'm going to show you here, b bar is equal to integration of dbx, that is along bx, that will become along x-axis bx into I cap, that's unit vector along x direction is I cap. Then mu 0 by 4 pi I into r divided by x square plus r square whole to the power of 3 by 2, integration of dl into I cap. So we are going to integrate it. Why? Because we want for the full loop. To find out for the full loop, we have to integrate it. When you integrate, the terms which cannot be integrated will be taken out. Whatever that is to be integrated will be kept inside. Only dl is to be integrated. So within this integration, we kept only dl into I cap. Then we are going to get, when you integrate dl, so as I have shown you, this is the full circle. Then dl is on the top here, another dl, another dl, another dl, another dl. So like this, if you integrate it, so continuously if you integrate each dl like this, one small part, if you take like this, finally it becomes the circumference of the circle. It becomes the circumference of the circle. Then integration of dl is equal to 2 pi r, because capital R is the radius. Integration of dl is equal to 2 pi r. Therefore, integration of dl, in place of integration of dl, integration means summing up all dl's around the full loop, all dl's around the full loop. It is nothing but circumference of the circle, which is equal to 2 pi capital R. Then let's continue. When it is 2 pi r, we will get 2 pi r, the mu 0 by 4 pi, here I am showing you with the red box, mu 0 by 4 pi, denominator I into capital R, integration of dl will become 2 pi r divided by x square plus r square whole to the power of 3 by 2 into I cap. Then we are going to get mu 0 I capital R square, because this pi will be cancelled out. In this numerator pi and the denominator pi, it will be cancelled out, and 2 and here 4, it becomes 2. Then finally you are going to get this formula, that is mu 0 I and then r into r. I'll remove these blue lines. So numerator pi, denominator pi cancelled. This 2 will cut it 2 times. Then you will get mu 0 by 4 pi, then I, r into r, it will become r square, then divided by, this will become 2, then divided by x square plus capital R square whole to the power of 3 by 2. This is you are going to get, and I cap. I cap is because it is in the direction of the x axis. Then after that, that is the formula. Then finally, if you go back once again, this is the one which we got, this formula. This is the main formula which we have derived for the magnetic field on the axis of the circular loop carrying current I. Mu 0 I r square by 2 into x square plus r square whole to the power of 3 by 2 into I cap. So remember this formula. Now in this special case, suppose this point P is at the origin, then this distance x will become 0. As a special case, suppose if this point P is here near the origin only, that means origin and the point P both are coincided. In that case, x is equal to 0. Then substitute x is equal to 0 in this formula. Which formula? This formula, that is mu 0 I r square by 2 into x square plus r square whole to the power of 3 by 2. In this, in the place of x, here in the place of x now, you substitute 0 because the distance will be 0 when the point P lies at the origin. Then what happens here is, then denominator, it will become r square whole to the power of 3 by 2. That is r square whole to the power of 3 by 2, and 2 and 2 cancel, you will get r cube. Then mu 0 in the denominator, in the numerator mu 0 I r square by denominator 2 r cube into I cap. I cap is the unit vector along x axis. Then r square and 1 in r cube 2 r square is cancelled. 1 r will be remained. Therefore, you will get mu 0 I by 2 r into I cap. This is the formula for the magnetic field at the center of the circular coil. This is the formula for the magnetic field at the center of the circular coil. So what we have done today is, we have derived the expression for the magnetic field on the axis of a circular coil carrying current. At the same time, we have also derived the expression for magnetic field at the center of a circular coil carrying current. Thank you for watching this video. If you have any doubts, you can send a message in the comment section, and you can also personally contact me and I can clarify all your doubts. We are there to help you for every problem. So thank you for watching this video. We will meet in the next video with another topic. Till then, bye. God bless you all. Bye.